So the first thing to say is that we're building on a programming language by Niels Nilsson, who's one of the gurus of AI robotics, right? Going back to the 1970s, the Shaky robot, which was the first robot that he gave a high-level goal to, and it worked out a sequence of actions using the STRIPS planning system. And the STRIPS representation of actions is still the base of automatic planners today, so it was quite seminal work. Anyway, what he wanted to do was to get a programming language for robotics that was the declarative equivalent of an analog controller, like this box here, where you have this sort of continuous inputs from your sensors, but of course they vary all the time, and they go through this analog control box, and then you get outputs, which change only when the inputs change. So the outputs are persistent. So in other words, if it's like drive at a certain speed, then you persistently drive at that speed until the inputs tell you to do something else. And of course, there's a feedback in the environment, because if you're acting on the environment, you're changing the environment, and then you get new sensor readings. Okay. I won't bother with the more details, but the final thing was he was on sabbatical, Nielsen was on sabbatical at Rodney Brooks' lab in MIT in 1990, and he was influenced also by the subsumption architecture, which is this sort of hierarchy of behaviors. You'll see that influence. What else? Okay, yeah, I think that's enough to say. Okay, so when you want to map that idea into a declarative language, you've got to have a way of symbolically representing the sensor readings, right? And so what we have is the idea of an agent, robotic agent, of the belief store, and in the belief store are these rapidly changing facts representing sort of possible relatively high-level interpretations of the base readings. So, for instance, the C bottle left 30 is an analysis already of a camera image. You've done some processing on a camera image, and you know that in this environment, say, bottles are all the same colour. This left means that the sort of the centroid of all the pixels of that colour is on the left of the central line of the camera, and by calibration you've said, if all bottles are the same size, then this must be a bottle 30 centimetres away, given that size of the image. In fact, we did that using an Android phone on a Mindstorms robot. Okay, holding, of course, is just sensors on some sort of gripper. Okay, so the idea is these things are coming in, and they're rapidly changing, possibly many times a second, up to 30 times a second. Right, so what's the control? The control is something that's sitting on top of those things and monitoring them reactively. Okay? And it's basically a collection of procedures, parameterized, as in normal programming languages, and each procedure is a sequence of guard action rules. Right? And the guards are queries to the latest batch of percepts. And the actions are either primitive actions, like close gripper, right? Or they're a call of another procedure, a telerouting procedure. So you basically cascade down and try another set of rules. Okay. Right. So what's the operational semantics? It's actually quite simple. You've invoked a procedure, right? And always you fire the first rule in that partially instantiated procedure, because you've given parameters. Those parameters will partially instantiate the rules. You fire the first rule, whose guard is inferable from the current set of percepts. Right? And that will be either a primitive action in which you do it, right? And you send that action out, and that continues, or is done, whatever. And if it's a continuous action, it carries on. Yeah? Or it's a procedure call. If it's a procedure call, you do the same thing. You partially instantiate a set of rules, you fire the first rule, and so on, all the way down until eventually you must hit a rule that actually is fired as a primitive action.
Why partially instantiate?
Sorry?
Why partially instantiate?
Oh, well, it's just like when you call a normal procedure in a programming language. When you pass the parameters in, basically you're given values to the parameter variables. Right? So it means that this guard will have both variables that are parameters to the procedure in, and it will variables that will get instantiated when you query the percepts. You'll see an example in a minute, right? Yeah.
Also, you said it's the first rule that fires, so the conflict resolution.
No, it's always the first rule that's fired. That's the simple thing, right? So that's the conflict resolution, if you like. if there are several rules that can fire. And typically there will be more rules later that can fire, but you fire the first one.
And maybe not the best one.
No, but that's the simple semantics, and it means you can be very fast about implementation. So, and you can get away with it for the most part. I mean, we can discuss this. You know, in fact, future work is to worry about that, right? But at the moment, it's always the first rule, right? Yeah.
So actually, there is very often some people try to do the implement refraction structure. There's the last rule that's fired never fires again.
In our case, we allow a rule to fire again, and that's important, and we call it refiring. Yeah. No, so we're not so. In fact, it's quite important that you allow refiring in our operational semantics and in Nielsen's operational semantics. Okay. So what happens then? You determine some primitive actions, and your percepts get updated. What must happen now? So this is the reactive bit. You reconsider every rule firing, starting from the firing of the initial procedure, right? So you start with the initial procedure, and you might decide to call an entirely different sequence of procedures as a consequence of that. What's the teleo bit? What's the goal seeking? Well, if you look at this sequence of rules, and I'll give you an example in a minute, the lower rules in a given procedure should be such that the action, when you execute it, when you fire a rule, a lower rule, the action should normally bring about a state of affairs in the environment such that guard of an earlier rule is inferable. Right? So that's the goal-seeking thing. What does that mean? It means that typically the first rule of every procedure has a guard that corresponds to the goal of the procedure and an action that says do nothing. Right? And we'll see an example of that. Okay. Right, now those two things, that goal-seeking and reactiveness, make these, this is a symbolic programming language. It enables you to program very robust and opportunistic things. In fact, it recovers automatically from adversity, as we'll see, and it's actually very good for robot-robot and robot-human cooperative tasks. Okay. Now, little icing on the cake, you don't have to just have the raw percepts coming in. You can have views, you can have relation definitions defined on top of that, and in fact you can have recursive relations defined on top of the percepts. And if you want, you can throw in a declarative model of the environment. So you can be interpreting the sensor readings relative to some knowledge about the environment. Okay, so this is reinforcing that picture of the hierarchy of invocations, right? So we start off calling this P procedure. This is the top level task that we want some robot to do. And H1, the guard of the first rule, which is possibly a deductive query to the percepts, corresponds to the goal. Right? When the goal is achieved, you do nothing. Right? The next one in this particular case is do in parallel a pair of robotic actions, A1 and A2. The third one is invoke a sub-procedure. Right? So, and that's what I've shown. I've shown Q being invoked. So typically, the initially invoked procedures do quite a lot of inference down onto the percepts, right? So they're deciding, maybe also querying the declarative model of the environment, which in the current circumstances, given the intention of this procedure, is the appropriate sub-procedure to execute, right? That's the Q. The Q then also has maybe some inference from the percepts, and that's deciding what purely reactive procedures, and of course this can be nested to any depth, but I've just done 3 here, and finally you end up typically at procedures that just directly query the percepts, and they're the purely reactive. Now I've shown in this particular case, well, suppose now all of a sudden H3 from the new set of percepts isn't the first inferable guard, and some lower one, H1 is. What does that mean? That would correspond in this sort of goal-orientated world to adversity. Something's upset the environment. And so something that's sort of like been achieved already, the H3 condition, in progression to H1, right, has been undone, right? So something's gone wrong. And so this flips back to a low-level rule, which should climb back up to H3 or climb up to H2, right? That's what will happen. But when you do drop down, immediately you kill Q and you kill R and you start a new hierarchy, right? So procedures, telereactive procedures do not terminate themselves. There's no exit, right? they always get terminated by a parent or ancestor, and they're also, the default is they're persistent. So this P thing will just sit there monitoring H1. And if H1 changes, it'll start doing something, right? So in goal-orientated terms, they are actually achieve and maintain, right? They're very good for monitoring an environment, and as soon as it becomes unstable or the achieved situation is undone, it will actually try to be achieved. Okay, now a concrete example, right? Silly little bottle collector, green bottles, red drop area. What I want is to write a program that will find a green bottle, look for, go to, grab, and deliver the green bottle to the red drop area, and then just sit there like a dog that's retrieved a ball until the thing disappears, and then it will go and find another green. Okay? Right. So this is the top level collect bottle. You always start, you work backwards, you work optimistically. Well, suppose I've already got the robot sitting in front of a bottle next to the drop. I'm done. It's as though you start off and already the ball is at your feet and the dog's there sitting waiting, right? And that's the first rule, and that corresponds to the goal. So it's have delivered. Have delivered is defined now. So the green things are the percepts, the deep blue things are my defined views on percepts, right? So have delivered basically is going to be relative to the low level percept of the camera image interpretation, that you can see the drop in any direction at zero distance, you can infer you're next to a bottle, and you've got the percept that tells you the grip is open. So that's like the dog's opened its mouth and he's dropped the ball. Okay. Next, the bottle is, you can see the bottle in some direction, and either direction for another reason, and the distance is less than 2 centimeters, right? Right, so if you can infer already you've delivered, you're done. Right, and then you just chain backwards. It's like regression. What is a next best thing? And there might be several next best things. This one's linear, but in general it's a tree. It's a tree of sub-goals. Well, if you can see the drop at zero distance, but you can still sense you're holding something, then what you've got to do is open your gripper. Because if you open your gripper, it should be the case that in the next round of percepts, you'll get the percept that the gripper's open, and you will be able to infer have delivered. Right? So that's that goal achieving. Right? Should be that action will achieve the goal of the initial rule. Okay. What's a next best thing to that? Well, that you're just holding something, right? In which case, the goal, what you've got to do is to get to the drop, right? Now, I don't have a primitive action for getting to the drop, so I'll say, right, I'll write a procedure. I'll write a sequence of rules that will, whilst holding remains true, get me to the bottom, right? And indeed, it must be the case that whilst deliver bottle's executing, holding will remain true, because if holding became false, that would no longer be the first rule with an inferable guard, and I'd do something else. So for example, the last rule, true, get bottle, which is the default rule, so you're not even holding, you're not on the drop, nothing helps you, right? Then you invoke the sequence of rules, get bottle. That would mean that whilst the robot is holding the bottle, and it's being controlled by the deliver bottle procedure, if it drops the bottle, it will automatically invoke get bottle to pick it up again. It just comes naturally out of the operational semantics, right? Because that will not be the first rule. The holding rule will not be the first rule. It will default and try to pick up the bottle again.
What if the bottle breaks?
Sorry?
What if the bottle breaks?
Well, it's smashed, and it'll look for another one.
It's interesting.
No, it'll look for another one, right? And yeah. Anyway, look, I'm assuming rubber bottles here, right? No, don't make it too difficult. Okay, so deliver bottle is very similar, but remember holding will always be true. So if you see the drop at zero distance, you're done. If you see the drop at, remember the second rule will always be that the distance is greater than zero. I actually don't even need to put that distance greater than zero, because if I get to that second rule, then I know the distance is non-zero. Then I invoke approach. Now this is a parameterized one, right? Because I'm going to use, approach is used both for approaching the drop and for approaching the bottle. I haven't given you the get bottle, but the get bottle is very similar, and it also invokes approach. The default rule of this procedure is just a turn. So basically, when it's starting, and it doesn't see the drop. It actually turns on the spot until it sees the drop. As soon as it sees the drop, it starts walking towards it. Okay, now approach. That's interesting. It's got two rules. In fact, whilst approach is executing, I know that the thing being approached is seen. Right? It will only be executing while this is seen. And it basically has two rules. One says, if you can see it roughly in the center of your field of view, then move forward at some calculated speed, which depends on the thing you're approaching and the distance. Right? Now, why do I want to make it dependent on that? Well, I want it to slow down more when it approaches the bottle than when it approaches the drop, because I don't want it to knock the bottle out of the way. Right? So the approach, and moreover, I want it to slow down as it gets closer. So I want to invoke this as a function that gives me the forward speed. Right? And then the second rule will only be used if the direction in which the thing is seen is left or right of the center. Right? And center is actually for us, in our implementation of this, plus or minus 10 degrees. And what that does is exactly the same with respect to the forward speed, but it also turns in parallel, a parallel turn action, to bring you back into the center. It turns in the direction that it's seen. Okay, now, so that basically was Nielsen's language, except he didn't have the function called calculate speed. But if we're going to send these things out to a real robot, we have to worry about some things. We have to worry about the fact that we're going to send an action, a speed action, which is a number. So we want it to be that computes, that calculate speed computes a floating point number, right? And the distance is going to be a number, a floating point number. And then when I send a turn command, through ROS maybe as a string or something, that I'm actually only using the names, the strings for direction that the ROS interface will understand. Right? So that basically means we should type. We have to type. The type system, we have to have a type system both for the procedure parameters and in particular for the rule language. Right? And that's basically what we did, one of the things we did. Okay, so this is the architecture as it stands. It's a two-thread architecture that we have, and you have a percepts handler, which is a dedicated thread that's just waiting for fresh percepts to come, notifications from ROS or something like that, or from MQTT. We've got an MQTT interface. And every time it gets a batch, it does an atomic update of these percept facts in the agent's belief store. Right? Now, above those percept facts is a rule hierarchy. Right? And as you go up that hierarchy, you get higher and higher level interpretations of the percept facts, possibly making use of fixed facts, giving you information about the environment. On the right-hand side, you've got the action tower. Nielsen calls it the action tower. You've got initial procedures that you're going to start, and they correspond to high-level tasks that essentially query the percepts through that deductive belief tower. Right? They actually go down the tower to interrogate them. And they themselves invoke sub-procedures, and finally, they invoke purely reactive procedures at the bottom that directly query these percept facts. Okay? The telereactive evaluator, when there's an update of the percept facts, it reconsiders all the rules, or if it's just got one procedure, it finds the procedure to call, cascades down, gets all the 5 rules, and then sends out the robotic actions. And there could be a parallel set of actions that get sent out. It then goes to sleep until the percepts get updated, right, atomically. As soon as they're updated, it reconsiders all the rules, right? And again, determines new actions to go to sleep, okay? So that's basically the operational semantics. All right, so what did we do? We took that language and then we did things to it. And the first extensions, which I won't illustrate with a program, were just for single task agents, right? So I've already mentioned we typed and moded the belief store language. Why do you need modes? Well, because if you've got a logic language, you need to know if certain arguments are input, certain outputs will be, if certain arguments of a relation are ground inputs, and those fully instantiated inputs, the outputs will be ground and things like that. That's the mode information. With a function, we always assume that, right? A function will always have fully instantiated inputs and will return a fully instantiated output. But when you've got relations, you need modes. And basically our language is called QLog. I could talk about that another time if you're interested. And it's a typed higher order hybrid of logic and functional language, and it's also flexibly typed in the sense we have subtypes and we have type unions. Okay, so that's it. It's a rich inference language for the agent's belief store. Okay, we also tweaked the form as rules, right? So we added 2 extra forms of rules by allowing you to have, as well as the guard, you can say, you know, guard while C do, and then you can say guard until you do. Right? Now what do? They're rather like what Rodney Brooks has in his behavioral architecture, subsumption architecture, inhibitors. The while C inhibits the firing of rules below should the guard become false. So it's basically saying, hey, look, I know what I'm doing, I've fired this rule, and actually it's likely that the firing condition will become false, but I want to persist while C remains true. I actually will give you an example of that later. Until is the dual. It says, I fire this rule, the action will start executing, and it might, too early, achieve the guard of a rule above. And I want you to delay jumping to the rule above until u's true. Right? So basically the while prevents too early re-achieving, and the until allows overachieving. And just let me give you those in broad terms, right? And I'll give you one example of
So this until is a sort of security measure to be this until operator is a sort of security measure that allows the rule to be fired again and again.
No, it's not being fired again. It means that don't switch to another rule until u is true. Don't jump up. You know, because remember we're always jumping up and down because we're always doing the earliest rule. It's saying don't apply the earliest rule condition while these are, it suppresses that earliest rule condition
So
basically.
while stops you going down and until stops you going up.
Exactly, yeah. And if you do the 2 together, it basically says, beaver away on this rule! You know, it's like a sort of ballistic, it's almost like a ballistic action. Until both the... so we actually have a construct while until, where you give one condition, and it basically sort of saying, ballistically, whilst that condition holds, do not go above and do not go below. Mind you, interesting enough, that only applies it's local to a procedure. If the parent says, don't do this at all, you exit, right? Parents are always dominant, right? Because it basically means you shouldn't even be doing that. So forget messing about, right? It's just a local thing. And that's important for the semantics. The semantics is cleaner if you have it local. Okay, I'll give you an example of the until later. Right, the other thing we added was, at the moment, you either, in Nielsen's language, you either had a call of a telegraphic procedure, or you had a conjunction of primitive actions, a parallel conjunction of primitive actions. Sometimes you need to have an action continue for a time, because there isn't always a perception to determine when you should switch, right? So we basically added time sequences. An example of that is wandering behavior, right? You want to go in a direction for a certain time. When that time is lapsed, you want to change the direction and wander around, right? There isn't an obvious thing to determine when you should change direction. So we added that. And that includes time sequences not only of primitive actions, but times inside that time sequence you can have telereactive procedure calls, right? So it's actually quite powerful. Again, I won't give you an example of that. I will give you an example of this one, wait repeat. And it's particularly useful for discrete actions like open and close grippers. I won't say more, I'll give you the example. And then the other thing we added was, well, when you do an action, you might want to remember something. You might want to remember you've done it, right? So as well as actually doing the action, you can concurrently or at the same time update your belief store, or actually remove something from the belief store, right? And we wanted to have this for cooperative robots, where there are several agents controlling different robots. We allow message send actions. And we don't consider that, we decided not to make that a robotic action, because we view it as coming for free, right? You know, the internet, right? So it isn't using a resource, it isn't using a physical resource. So communication actions, message send actions, and belief store updates are separated from the normal robotic actions and the procedure calls. Right, let me give you, okay. come back to the weight repeat. Okay, so if you have communication, the architecture gets a little bit more complicated. You actually have a message handler in the middle. So as well as something that's monitoring the sensor data and doing atomic updates of the percept facts, you have something that's waiting for messages from other agents. And depending on how you program it, and percept handler and message handler have to be programmed in a different sort of language. In fact, they're programmed in this QLOB language, in the action rules of the QLOB language. That can also update the leaf store. So you can have other agents telling. Now, I used to have, but I didn't have time. I always used to run out of time. An example where we took that bottle collecting thing, and we had 2 agents controlling 2 robots, and they had a joint goal of collecting 20 bottles. Right, they have to communicate to tell one another when they've delivered a bottle, so they both know when 20 have been collected. So that's one communication. I also made an assumption that they had very poor vision, and when they could see the other robot, and they could see it was near, but they couldn't tell whether it was approaching them, going away, or moving sideways. Right? They just see a blob of colour. Right? So what happened is they then use communication to avoid collision. To avoid collision with minimum avoidance. Right? And one of them, as soon as it sees the other one, says, hey, it stops. The control program stops, sends a message to the other one saying, I've stopped and I can see you on my right. If the other one's tracking across, it basically just remembers that information but carries on. And eventually, if it is tracking across, it will disappear and the other one will carry forward. Right? If, however, they're actually facing one another, they both will exchange messages saying, I've stopped and I can see you on my right. I've stopped and I can see you on my left. If they say that, they can just carry on slowly. And so, right? So we've got this little avoidance program which involves communication. So in that case, communication is used to overcome poor vision. Okay, right, so that's the picture. We've also got a quite nice communication server that links all this together, which we implemented a few years ago, based actually on Prolog technology. So the subscriptions are basically Prolog rules with patterns, term patterns, and conditions using a set of Prolog primitives. And it's a publish-subscribe, it's a combination of a publish-subscribe message router and address messaging. So, for instance, you can ingest other agents, like that thing there, agat host. You give each agent a name, and it's just like an email address. So you can send a message to a name one, or you can just do a notification, and it would just automatically get routed to every other agent that's got a subscription. So that turns out to be quite useful. Okay, a little extra picture. We haven't done this yet, but if you have a multi-threaded architecture with a shared store, it lends itself adding all sorts of extra capabilities relatively easily, right? So for instance, I can have a thread that's doing SLAM, and it's just monitoring some sort of low-level perception. It's trying to actually generate a model of the environment and localize the robot in that environment. I can also have an abductive reasoner that's trying to get more high-level explanations of what has been observed. Right? Now, what's the interference? Well, those things can be written completely independent of these guys over here, right? I can just plug them in. What's the connection? All I need to connect them is to know what predicates are going to be used by the SLAM and the abductive reasoner. So they have to be representing their obtuse and model information using facts, right? And I know, and I just have to say, okay, these are the ones they're going to use, right? So what do I do then? My Teleo programs have rules in them that have guards that query these predicates, right? If those things are not running, no matter, those guards will never become true, and those rules will never be fired, right? It's robust, it doesn't matter, right? They'll just be skipped, because they won't be the first rule in a procedure, in each procedure that has an inferable guard. But as soon as those guys start kicking in and putting those facts in, those extra rules will start firing, and I'll get improved behavior. So we should automatically and gradually get better behavior with the same program. Okay, here's an example of the weight repeat. Okay, so this was the top level collect bottle, right? And it had this open gripper. Now, suppose the gripper is stuck, okay? It should be, remember I said the open gripper should achieve a situation where the guard of the first rule is inferable. Well, suppose after 2 seconds, the evaluator, the Tellure evaluator, has not switched rules. Richard, you got any sleep? Am I so boring? Right. So that basically is saying to the underlying system, if after 2 seconds you still want to fire this rule, right? Repeat the action. What does that mean? Send it out again to the robot, right? And hopefully it'll kick a bit of hardware or something, or fire another current or something, right? And I'm basically saying, do that 3 times. So if after 8 seconds and 3 repeats, you haven't managed to jump to that rule, have delivered, right? It's an error condition. What do I want the system to do? Well, it's quite easy. I just want it to put an error fact in the belief store. That's all it needs to do. Right. How do I... So that's like a throw. How do I catch it? Dead easy. Instead of actually starting my top-level task with collect bottle, I start it with collect bottle wrapper. Oh, sorry, I'm missing a bracket. There should be a bracket after wrapper before person act, right? And I give that an argument, which is, I call it a Pedro handle. It's the address, like the email address of some, personal agent on a phone or something, or a laptop, right? Of a human helper. Okay. Now, when I start the bottle collection, first of all, there isn't an error fact in the agent's belief store, so it will just start executing collect bottle. As soon as that error condition arises, that fact will go in the belief store. Remember, we're reconsidering every rule of every procedure all the time. So we will immediately jump to firing that first rule. Right. That will actually do no robot action, and the robot will basically be suspended where it was, stuck there with the bottle in its hand next to the drop. That's what will happen, right? And I'll send a message, gripper fault, to Personac. And I'm hoping this person will go out with an oil can or something, right, and do something about it. Okay. All that I have to assume then is that that person, via his PDI or something, will send a message back to my agent's message handler. Oh, sorry, I've gone the wrong way. This guy over here, right, to say gripper fixed. No, the middle one, sorry, the message handler. I have to have programmed that, I have to have programmed it, so that when I get that message, gripper fixed or something, I remove that error belief from the belief store, right? So I have to have programmed it, I have to have anticipated this, right? As soon as I remove the belief from the belief store, right, the second rule will fire. It will cascade down, and providing the robot hasn't been moved, basically it'll be there with an oil gripper, and it will attempt to open the gripper. So we should have automatically recovered from where the thing is. And I've just used the evaluation mechanism of this language. I haven't done anything special. I've just used the operational semantics of this programming language. Okay, right, so now the topic of the title. What I want to do now is to have a single agent with one belief store executing several top-level telereactive procedure calls, which will be tasks, running them concurrently, sharing one or more robotic resources, right? Now, if you do that, of course, you've got to have the robotic resource mentioned in both the procedure calls, like collect bottle robot 2, and in the primitive actions, move robot 1, okay? So they become arguments of these things. The names of the robotic resources are very important. So actually, in our belief store language, it's a special type. We have a special type resource. I'll come to that in a minute. How do I control the allocation of the shared resources across these multiple threads of the task, concurrently executing tasks? Right? Well, we use a concept called task atomic procedure. It's like a critical region. Right? You specify that certain procedures are task atomic. And what that means is two things. Before any task can enter a task atomic procedure, all the resource parameters that it might, all the parameters of that procedure call that are resources need to be free and available for that task. And I'll refine that a bit more, right? So it has to be that it can grab those resources. It then has, it then has exclusive use of those resources until that procedure is terminated by the caller or an ancestor. Okay? It should also be the case that no other resource needs to be used during any evaluation path of that task atomic procedure, because that way we avoid deadlock. Yeah? We don't want partially grabbing resources and then wanting more resources as you go along, right? You've got to grab them all. So we check all this at compile time. The other thing it should be that when the thing gets terminated, either the thing's been abandoned or it has indeed achieved its normal goal, and it's left the state of the world in a stable goal, sub-goal position with respect to that task. And it hasn't left the state of the world such that when some other task gets hold of one or more of the resources it's released, the other task will undo it. Right? That's the Nielsen concept. Now, how do the tasks get coordinated? Well, we don't have a central coordinator. We actually use, take a leaf out of the Lynda model, and we use the belief store as a Lynda tuple store. Right? So when a task is inside a task atomic procedure, right, and it's already acquired certain resources, it puts a belief running underscore in the belief store. When it's waiting for resources, because one of the resources it needs is mentioned in one of these running facts, and therefore it knows that it's not free, right? It actually has a belief in the belief store that says, okay, this task is waiting, the time it started waiting, and the resources it's waiting for. Okay. Right, so what's the model now? The model is this. You actually have the same message handler, percept handler, but now we have several evaluators, several tasks running concurrently. So here I've got task 1 and task 2. They're all, every time, even the waiting tasks, task 3 and task 4 up there are waiting, every task, every time there's a belief store update, either by the message handler or the percept handler, has to re-evaluate its rules. Why? Because it could be that task 4 that's waiting for R1 and R5 changes its mind and no longer wants to invoke that particular task atomic procedure that needs R1 and R5. Right? Circumstances could have changed. For instance, it could be that a belief has come in to say that R5 is out of commission. Right? So it will want to do something else, need to do something else. Okay, so we've got the task 1 using R1 and R2, task 2 using R3. Task 3 is waiting for R1 and R3, right? Providing it carries on needing and waiting for R1 and R3, it's got to wait for task 1 and task 2 both to be terminated, right? Or at least to release, which means the task atomic procedure in which they're currently executing gets terminated. And as soon as it gets terminated, those resources get released by the fact that those running facts get removed from the belief store. So as soon as those running facts get believed by the belief store, task 3 can say, hey, good, I can grab R1 and I3. Okay, but suppose just task 1 terminates its task atomic procedure first. Well, potentially task 4 could run, yeah? Because it needs R1 and R5. Now at the moment, we do a strict fair policy. I've done them in that order because I'm assuming that task 3 has been waiting longer. So at the moment, the scheduling is, you like, you cannot jump when there's a task that's been waiting longer that requires one of the resources you need. Now that's something that we can change. We can have priority of tasks, we can have deadlines, right? But at the moment, in a simple model, it just waits.
What if there are more than one resource available?
Oh, well, that's okay. But then they would be multiply named, you see. So it'd be robot 1, robot 2, robot 3, that's fine, yeah. And that's okay, you know. So, for instance, these R1s could all be different robots, right? They could all be the same sort of thing. That's okay. But, you know, you have to give them unique names. You have to know which one.
No, I meant if you can assign different resources to the same task, meaning that, for example, 2 robots are at the same distance from the object, and they could both be available.
Okay. So in that case, that would be in your guard. Your guard would do that. Your guard would basically say, hey, in fact, that's quite interesting. It's an interesting question, that. The guard can actually query the running facts and see which ones are currently used, and know that there are some other ones that can be used, and therefore choose that. So your guard would then choose your resource. The action is the call of the task optometry using the chosen resource, and that's what you do. You put the pragmatics in the guard. Yeah. Okay, now a little example. Good. I'm not behind time. I'm usually behind time. Okay, so this is a... yeah, okay. What I'll do is just start running the thing now. Right. Oh no, I'll tell you something about it. Okay, and I can use this thing here, right? Okay. So I've got one agent, one belief store, right? And in that belief store are going to be lots of facts that tell me the positions of blocks, right? So they're going to say on 14, table 1, and so on, right? As blocks get put on one another, then there'll be the adjacency condition. If I put that one on that, it'll say on 4, 14, and so on, right? So that's the basic percept. So some analysis of a camera image that will give me the adjacency of single blocks. Right. These are two arms, arm 1 and arm 2, and it's, think of it as a packing problem in a factory or something, right? I'm going to actually have 4 tasks to build a tower of 4 blocks here, another tower of 4 blocks, a tower of 4 blocks, a tower of 4 blocks, right? What makes it interesting? What makes it interesting is that some of the blocks that are used here are here and here, right? So a task building here will occasionally have to use this arm, what? To move a block over here. Why? Because also there's a constraint on these arms. This arm can only reach this table and that table. That arm can only reach that table and that table. That's why I call it shared. Okay? So we need now, at certain times, you can't say ahead of time, these tasks only use one arm. We've got this dynamic allocation of the arms across the tasks as they run. We also have another problem, that is these two arms can both reach the shared table, so potentially they can clash. Right? And I want to avoid that. How can I avoid it? I make the tables resources. Right? In that case, before a task can reach to the shared table, it has to acquire the shared table as a resource, and since there's only one shared table, only one task can be reaching to the shared table at any one time. Okay. I hope this works, because the other day I tried to run it. Okay. Right, okay, let me give you some little colour coding. There's some colour coding here. It might run too fast anyway. So these are the tasks down here. Task 1 is to build 5, 3, 15, 2. We've already got 15, 2, right? Built already. Over there we've got, task 3 and so on. So they're all colour coded. Why is table 1 now red? That's because at the moment, task 2 has got hold of table 1 as a resource, and it's got hold of arm 1, which is why arm 1 is coloured red. Yeah? Task 2, which is building on table 1, needed to fetch a block from table 2. So it's acquired arm 2 as a resource, and it's actually moving it across, I think. Yeah, what's it, can you see what it's picking up? I can't see it. 13 or something, is it? 10? Anyway, whatever.
I think 10. Yeah.
10, yeah. So it's picking up 10, which is actually the base of its tower. See, task 2 has got base of tower, and it's going to move it to the shared table. Right. Okay. Now, what I'm going to do is, what am I going to do? Let me do some. So what's happening here? Blue is going to pick up 7. Yeah, and it needs to put it on, where's it going to put it on? 6. It's going to put it on 6, which is the second partial tower, right? Okay, now what I'm going to do is I'm going to thwart it, right? I'm going to thwart it. I'm going to actually move that here, right? So it shouldn't be picking up 7 anymore, right? There's no point, okay? This one, 4, is picking up 4. Why is it picking up 4? Because it wants to put it on 10. I'll help it. Right? Now it should be that this guy will either stop and somebody else will kick in, and this chap should do something else. Yeah, okay. So we can thwart or help and it automatically will go. Now let me do something else. Let me do a real disturbance. Remember I said it was achieve and maintain. So I'm going to do a real disturbance here. So I'll move that there, move that there, move that there. So this chap here now has got to, it's got to reassemble its tower. It's got to get hold of this one at the bottom, right? Which is the base of its tower. To get hold of that, it's got to unstack all these, right? Okay, now, what's that one? I can't even see, what is it? It's 9, right? 9 is needed over here, right? So what it will do, of course, and the default thing when you're unstacking is just to put it on this table, right? So that's what it'll do. It'll put 9 on that table. What's the next one? 5. 5 is actually needed by this task on table 1. So if I'm doing smart compiling, I remember I'm inside one agent here, and therefore the tasks in the belief store, I've got meta information about what the tasks are and what towers are being involved, right? So if I'm clever, and I have been clever in the program, I can say, hey, while I'm on line 5, is that needed by another task that's actually building on table 1? Yes, it is. Good. So instead of actually putting it down on the shared table, I'll put it down on here, because that removes one need to access the shared table, and the shared table is a bottom. It can be even smarter. It so happens that that one is the very next blocks that's needed for this. So this task, even though that's not its main goal, because it can do it for free, as it were, we'll put it down on there. Finally, when it compiles this one, or initially when it compiles that one, it will say, hey, does the task need it? Yes, I do. So I'll put it down on here. I can't put it on somewhere, right? So we should have that. Good, that's on there, that's going on there, that's going on there, and there we are. Right. Okay. Right, so,
Was that something you specifically, so it taking advantage of the availability of that
yeah,
block and moving? Was
I
that
have-
coded specifically in this example, or did it just fall out of the
well,
architecture?
no, it's application specific. It's
Right.
application specific. I have to know that there are beliefs in my belief store that tell me about other tasks. I call it cooperative unclimbing. It's where one task can be cooperative. It can be smart. And you get that because you've got all the information in the one belief store. It's one of the advantages. If you did it by separate agents, it would be much more kludgy to do that sort of cooperation. Right, okay, so I'm not going to go into details. This just gives you a little bit of a flavour of the belief store language. I have to be a bit elaborate for this one. So these are some types. Blocks are 1 to 15. Table, I'm giving you this enumerated type for table. This is type union. A place is a table or a block. This is resource. I have to say what the resources are. The resource are the arm, the union of the arm type and the table type. All right? So in other words, the resources are named like table 1 shared table 2, and the numbers 1 to 15, no, not numbers 1 to 15, sorry. Place, oh, actually I need another type, sorry, I need another type. I should have said arm is arm 1 or arm 2. Yeah, I'm sorry, I need another type on there. I declare what the percepts are. I have to declare what the dynamically changing things are, and there's some example percept facts. And now we have to build up knowledge about what towers are, right? And I need a recursive definition of subtower. I can then define tower as a subtower such that the block on top is clear. I have to define what a clear place is. Every table is clear, and otherwise, if it's a block, it has to be there isn't another block on it, and so on. Right? This is like a very trivial sort of layer of defined rules. This then is the top level procedure, very similar to the others, starts with the same sort of thing. Am I done? Can I infer, so arm is the arm to use, the primary arm to use. In other words, it's the arm that can access tower table and shared table. That's what arm is. Blocks is a list of block labels that are to be configured as a tower. So, can I, from the current set of percepts, using my definition of tower, infer that the blocks are already configured as a tower on tower table? Yes, do nothing. Right. Suppose I haven't got it as a tower, but I've got it as a sub-tower. Well, if it's a sub-tower, it means the stack of blocks I need are there, but there are things on top. Right? So in that case, make the top block clear. Right? And I've got the, oh, I should say blocks rather than BS, there's a typo. So just unpile them, right? So if the second rule fires, the action of making the top block of that sub-tower clear should achieve the guard of the first rule, right? So that's the goal director. I've got the goal director. Right, the other one is another near miss. Suppose you've got a sequence of block labels, B, B prime, da da da, and all but the first one is already configured as a tower. In other words, if you ignore the first one, B, you've got a tower on tower table. Right, good. What I'm now going to do is invoke a subprogram that might need both arms to move B, the extra block, to be on top of B prime. Right? And that might involve reaching, and it might involve going to a shared table. But if that succeeds, it should be the case that I will achieve the guard of the first rule. So the third rule will also leap if it succeeds to the guard of the first rule. Right, this is the recursive procedure, so this is the base case. Suppose I only have to configure a list of blocks of one block. Well, the problem is I've just got to get that block from wherever it is and put it on the tower table. Right? And that's what that's doing, right? So again, using the possible two-arm move, except instead of the destination being a B prime, the destination is the tower table. Finally, I've got nothing to help me, right? There's nothing helping me. Right, what do? I factor the problem. I ignore the first block, I recursively invoke this procedure to configure all the remaining ones, and then what should that achieve? That should achieve the guard of the third rule, right? I should have all but the first block configured as a tower, and then the third rule will kick in, and it will move that thing. Okay, so it's very simple. Right, I won't give you too much more detail, but this is the task atomic. This is the one that requires that gets resources. The pos2arm move does 2 calls to task atomic to basically achieve the move. Task atomic has, what, 5 arguments. It has the arm to use, the block to be moved, the table where the block is, the place, and the table where the place is. Now, if place is a table, the last 2 arguments are the same. But place can also be a block, and it tells me where that table is. So it could be that I use arm 1, block 3, table 1, place is block 4 on table 1, say. Right? And that's basically moving it from actually on the same table. And again, it's the same sort of thing. And here's an until. Oh, it's an until I'm in the string, sorry, not one. If you've got the block on the place you want it to go to, or it should be place, I'm sorry, I edited this morning and I didn't edit it. That should say place, you're done. Otherwise, if the place you've got to go to is clear, and the block's clear, then this is a little simple sub-procedure that doesn't need to worry about unpiling, and it will just grab the block and put it there, right? Because they're both clear, and that's not a problem, right? Otherwise, I might have to do some unpiling, right? So these are the 2 rules that do unpiling. Suppose the 2 place is clear, that means it's either the table or it's a block which is clear, I don't have anything on top of it, right? Then what I must do is unpile. It must be the block isn't clear, because I've got to the 3rd rule, so it must be the block isn't clear. I must unpile block using block table to put the blocks on, right? And I'll carry on doing that until the arm is not holding anything, right? So I don't want to jump to the above rule too early, right? Because I want to, why? Because I want it to be that when I invoke clear 1-arm move, my arm isn't holding anything. So I'll make sure that unpile does the unpiling, and eventually it's unpiled the last block and it's actually put it down. And only when it's put it down will I jump to the 2nd rule. Right? I want to delay until that unpile has put that last block down. Because otherwise what I'll do, as soon as I pick that block up, the thing will be clear and I'll jump to the other thing. And I don't want to do that. I want to delay until it's actually put it down. That's a very slight delay. And then finally the last one is where you clear place, and it's just exactly the same until you're not holding something. So I want to really make sure I've finished the unpiling, and that means I'm not holding anything anymore. Very, very slight use of until there. Right, okay. I should stop really, but just let me say we've got a formal state transition semantics. The implementation is faithful to the semantics, and what was interesting, the semantics and the implementation were developed concurrently, and there was a nice to and fro. And in fact, in particular, which is what you hope, when we got the semantics right, we realised our implementation was wrong. And in one case, we had a conjectured semantics for something and we couldn't implement it. So we had to weaken the semantics. So it actually was a very good exercise to do them both in parallel. The moment we're going to have an abstract, a special abstract machine, unless it's just some future work, in particular uncertainty and probabilistic reasoning and constraint handling. And then related to your question about not firing the rules in order, then if we have uncertainty, there's a notion we've got of clustering or grouping a set of rules that are guards that are only inferred with a certain likelihood. And you have that likelihood, and then you can also associate a likelihood of success of the action, right? And then you basically can, in parallel, well not in parallel, but do all those guards at one, not choosing. Look at the degree that you believe the guard is true given the percepts. Look at the likelihood that the action will succeed in its intended, to achieve its intended goal, and then make a decision. Right? So you make a decision on some product of those two or whatever, right? That's a little pragmatic decision. So that's one thing we thought of doing. Okay, I should stop.
Could you just say something about the sort of practical architecture in terms of where the interfaces with ROS would come and
Sorry, so where
the interfaces with ROS would come?
Right, okay, so the interface with ROS is,
runs and
yeah, it's sort of outside these pictures anyway. Oh, why is it gone like that? That's gone like that. Yeah, okay, so let's look at that picture. It's basically what we've got at the moment. We've got this thing, both these things, if we've got the ROS interface, actually come from and go to Python process. At the moment, that's what we do, right? We haven't got very tiny integration. We use Python, we piggyback on Python, because Python's got a very good ROS interface, right? And we've got a very good Python interface. So that's what we do. So we sort of cheat, right? So we have to know, if you like, what that Python does. It does the work of converting from, make an assumption, well, whatever the ROS notifications are that come out, it converts those to strings that we can push to our percept panel. Right? It does the work of stringifying and getting the strings that represent the percept facts. And correspondingly, when we push out our robot actions, which actually go to strings, and go as strings, it does whatever is needed to do the notification to the robot resources. Yeah. So it's below that picture. And the same with MQTT.
I spent quite a lot of time looking at these subsumption architectures in an inductive sense. So we're using, again, this mechanism of progressive instantiation, but doing it essentially top-down to explore the environment, to use it exploratively. Because you've got to then have some capability for producing new percept facts and higher-level percepts to do that. But it strikes me that it really is something that lends itself to distribution using some underlying mechanism like that. I don't know if you'd have, if it were relaxed to the point that you could do this inductively, essentially, with these perception action hierarchies. If there's some particular relaxation of the behavioral architecture that you might need in order, for the collective pooling of beliefs, for instance, about higher level.
Well, it's interesting you should say that. So there are two ways in which you can get collective beliefs. That is to allow one control process to be streamed, to get in all the sensors and doing the control by multiple threads. Then you've got more than one store, right, which is what I've illustrated here. The other way is you do it with separate agents, and then you've got to cooperate. You've got to have the agents telling one another, right? Now, there is a guy who is a postdoc at Imperial who used to be in the logic framework. In fact, for his PhD, he did a distributed abductive system. And he's done a really neat thing, which I'm waiting for the paper on. He's used a distributed algorithm, just like our sort of resource allocator is like an algorithm underneath the bonnet. He's done an algorithm underneath the bonnet that will homogenize the belief store of separate agents. Right? So you can link them. They have to be obviously in a cooperative club, right? But that will just happen. You don't need to worry about it. You don't have to do explicit communication. You just have to say these things need to know about what they all know about. Right? And he